Welcome to Senior Developer in 24 Hours. My name is Andres, and today we're going to be talking about how we can write high-quality code. This is part 14 of our series, and so, let's dive right in. Okay, so what is the main takeaway of this video? We're going to be talking about high-quality code, but exactly what does that mean? So the first thing we're going to do is we're going to decompose the notion of high-quality code. What exactly does it mean? Then we're going to go into some metrics that we can use to actually measure quality so that we know that we're making progress. With that said, well, we know that all code should be high quality, right? Maybe not. Obviously, there's some code that we write that is, throwaway code. There is code where we want to polish. We want to make sure that it is something that will be useful in the future. So in here, we're going to focus on the code that we see as long-term code, and for which we want to make sure that the quality is right. So with that said, what are the qualities of high quality code? Obviously, it has to be functionally suitable. It has to be reliable, it has to be readable, maintainable, reusable, it has to be simple, it has to be scalable, and of course, as we've talked in previous sessions, it has to be testable. So with that said, let's go into the different categories of what makes a piece of code high quality. The first thing, and this might sound obvious, but obviously we still want to cover it here, it has to be functionally suitable. It needs to be able to fulfill the functional requirements that we have received. It has to be able to fulfill those requirements with accuracy. And, it needs to meet whatever functional compliance requirements that have been set by us. Whether it's a standard, whether it's a particular acceptance suite that we have to pass, all of those things need to be adhered to before we can even go into some of the other topics. So obviously, functionally suitable is at the top of the list. If the code doesn't work, it doesn't matter how well structured or any of the other metrics apply. It also has to be reliable. Here, we're talking about things like maturity. We want to make sure that we're fault tolerance to ensure that we're meeting the reliability requirements. And we're going to go a lot deeper into reliability in a future session. We have a whole session on reliability. But for now, as we're thinking about high quality code, it needs to be fault tolerant to be able to meet the reliability requirements that have been defined. And in here, we're venturing into non-functional requirements. Before we were talking about functional requirements, the requirements that we have to meet to achieve the functionality requirements. Now we're talking about the more ambiguous non-functional requirements, of which quality or code quality is one of those. Other things that we care about when we're talking about reliability, we talk about, hey, can we recover from hardware failures, from component failures, things like that. Do we have any reliability compliance that we have to meet within our organization? All of those things are things that matter for us to say that our code is high quality. And again, we're going to talk a lot more about reliability in a future session. So for now, let's just put it to the side. Now let's talk about readability. Make sure that we can actually read and comprehend the code. For this, we want to have thoughtful naming of variables, functions, things like that. We want to have relevant comments that are not obvious. If you're a developer, you can read the code. So we want to focus on things like, why do we do something a certain way rather than how are we doing it? Because the best description of how we're doing things is the code itself. So we don't want to replicate those things in the comments. Those comments tend to not be very useful. So we want to have relevant comments that are going to augment our understanding of the code. Obviously, the code needs to be well structured. We want to be as simple and concise as we can within our language. We want to ensure that the different modules, the different functions, the different methods have a single responsibility. We also want to focus on the lines of code. And as we talk through some of these concepts, we're going to talk about lines of code. We're also going to be talking about logical lines of code, which are, the code that does not include comments as opposed to just counting all of the lines in the file. So with that said, how many lines of code is too many? How many lines of code is too many in a single file? How many lines of code is it too many in a single method or a single function? Those are all questions that we can ask ourselves, that we can try to find some consensus within the group, and then make a decision to make sure that we are staying within the boundaries of what we consider reasonable for our code to be readable. Now let's talk a little bit about formatting the code. One of the most important things here is to avoid bike shedding. If you've never heard this term, bike shedding is when we focus too much on the easy things because we don't want to tackle the hard things. And bike shedding comes from this story about a group of bureaucrats in a committee trying to plan for a new power station, and they spent more time thinking about a bike shed than about the power plant because it was easier for them to understand. So code formatting is important and you need a standard. But with that said, pretty much anything will do. So you don't want to spend hours and hours, days and days debating which is the best one. Pick one, roll with it. As long as it's consistent, it will work for you. Something else that's important, you want to automate the code formatting. And because we want to make it easier for our developers, if we can automate code formatting using something like Git, straight up from the development stack that we're using, we can use something like a pre-commit hook to enforce formatting every time a developer is ready to commit a new change. So, something that doesn't add any overhead to the developer. We have a standardized way of doing things, and it will also reduce, for example, the devs that you're going to run into when you are committing changes to the code. All right, now let's talk about maintainability. How easy is it to fix bugs? How easy is it to add new features? How easy is it to add or make changes to the code safely? And when I mean safely, how likely is it for me to be able to go in and out, make a change, and not introduce an unintended consequence, not introduce any bugs? So how can we improve the maintainability of our code? Obviously, writing good code helps, but there are other things that are more specific that we can do. One of those things is to, for example, take a look at code duplication. When we're thinking about code duplication, if we have a lot of duplicate code throughout our system, it's going to make it harder for us to fix bugs. Why? Because we may fix a bug in one place, but not in another place, so we might have inconsistent behaviors. It makes it harder for us to add new features, again, because we have to add features in both places, or we have to figure out which place it's relevant, which one it isn't. Because at the end of the day, what we're trying to do is we're trying to limit the risk of any changes that we do. A code base in which we can make changes with a low risk, it's a fairly maintainable code base. If you have a code base where any little fix is going to cause a lot of unintended consequences, well, then we have a piece of code that is not very maintainable. Many of the issues that I've talked about regarding code duplication can be alleviated if we have good unit testing. But honestly, and this is my personal opinion, removing duplicate code will reduce the cost of all of this extra testing, and it feels good. It feels good to be able to simplify your code, reduce duplicate code, reduce redundant code. It just feels good. For me, those are some of the most satisfying changes or commits or pull requests that I can make. We also want to make sure that we don't have too many code smells. And code smells are basically maintainability related issues in the code that are normally caused by lousy coding practices. And when we have a lot of code smells, maybe the code is working fine. And in the best case scenario, if we have a lot of these situations, it is going to make it harder for our developers to understand the code and make changes. And in the worst case, it is basically going to make our developers so confused that they will end up introducing bugs when they make changes. And sometimes, we're talking about small changes. So here are some examples. For example, if we have methods that are very long, if we have a lot of dead code that, do we have to fix this code or not? Does this code is affected by some changes that I'm making somewhere else? All of those things. When we have very long parameter methods, when we have improper operations, when we're doing things, for example, that could have threading consequences or things like that. When we have loaders, and when I say loaders, I mean methods that have grown so much that, they become really, really hard to manage. So those are all general code smells that you can find in pretty much any language. Of course, there are some specific code smells to each language. So if we're talking about Java, we can talk about things like not preserving an original exception. When we catch an exception and we throw another exception, we are just ignoring the original exception. That can make it a lot harder for us to track errors and things like that. For example, if we are not overriding the equals and the hash code methods together, we can run into all kinds of issues using equality, using hash maps, things like that. When we're using things like print stack trace, which sometimes we do just for the sake of ease of use, but in the long term, it might end up printing things to the console rather than to whatever logging mechanism we have. If we're talking about Node.js, using the wrong kind of equality, using 2 equals as opposed to 3 equals, too many indentation levels, functions that do too much. If we're talking about Python, list comprehension within list comprehensions, empty exception blocks, using print for debugging. So again, lots of general things that could apply to any language, but we also want to understand the idiosyncrasies of each language so that we can avoid making mistakes that might make our code harder to maintain. Okay, now let's talk about reusability. Okay, the first thing with reusability is it depends on the purpose of the code. Some of the code is meant to be reused, some of the code is not meant to be reused. So we have to understand the context. And again, for most of the decisions we have to make, context is vital. And us as developers, we need to understand that context. It can be very subjective, but at the end of the day, if we're using proper object-oriented patterns, all of those things will help us have more reusable code. And these are things that, because they are so subjective, they are better enforced at code review time, where a reviewer can have the context of whether the code needs to be reusable, and whether we're building the code in which it can be reused in the proper way in which we foresee that code being used in the future. All right, complexity. So our code should be as simple as possible, but not simpler. Albert Einstein. Or maybe someone else. I'm not sure who really wrote that quote. Some people in the internet said it was Albert Einstein. Some people said it was somebody else. I don't know. But at the end of the day, the quote is still valid. As simple as possible, but not simpler. All right, so what does this mean? We're going to have simple code. We're going to have a lot more complex code, depending on which part of our application we're talking about. We need to be able to manage this complexity. That is the key piece here. So we need to be able to measure the complexity. We want to be able to track changes in this complexity. And we need to have a maintainable code base so that we can break apart the code when needed. And when I say needed, I mean when the code gets too complicated. All right, so there is a particular mechanism for measuring complexity of code, and it is called cyclomatic complexity. And it is defined as the number of linearly independent paths within a section of source code. It was developed by Thomas J. McCabe Sr. in 1976. This one is properly attributed to Mr. McCabe, and it has become a standard way to measure the complexity of our source code. So now let's look at some examples to properly understand what this means. All right, so basically, cyclomatic complexity is a quantitative measure of the number of linearly independent paths through a program source code. And here it is key to understand that, this is a quantitative measure, so we can get an exact value. So let's take a look at some examples. Here we have a very basic example. We have a piece of code, has 4 statements. No branching, no conditionals, just one statement after the other. This one has a complexity of 1 because there is a single path through the source code. Now, if we had something like this, where we have one branching statement, we have a cyclomatic complexity of 2. Why? Because we have 2 independent paths through the source code. The first one, we're hitting statement 1, 2, and 4. The other path, we're hitting statement 1, 3, and 4. Of course, the number is going to keep increasing as we go into more complicated pieces of code. For example, here we have a piece of code that has 2 independent branching statements. Here we'll have a complexity of 4 because we have 4 independent paths through the code. In the first one, we're hitting 1, 2, 4, and 6. We could also hit 1, 2, 5, and 6. 1, 3, 5, and 6. And finally, 1, 2, 4, and 6. So again, 4 different ways in which we can go through the code independently. And of course, to fully be able to calculate this, we have to have a good understanding of the code, make sure that they're truly independent, and so on. There is tooling that will help us calculate this so that we don't have to calculate it on our own. But it is important for us to at least have a basic understanding of how it is measured and how we can use this to manage the complexity of our code so that it doesn't get out of hand. All right, so as you can see in those examples, the lower the complexity, the easier it is to understand the code. And obviously, the lower the complexity, the less the risk. So how can we apply this? And these are some very basic guidelines that are normally used. If we have a complexity that goes from 1 to 10. We're talking about a simple procedure, a very little risk. Between 11 and 20, more complex, moderate risk. If we go between 21 and 50, we're talking about complex code, high risk. And, anything over 50, code that is pretty much untestable, very high risk. So where do you draw the line? Do you draw the line at 10, 20, 50? It is up to you. It is up to your team. But this will give you at least a broad understanding of what could be acceptable. All right, and also, as we try to tie everything together into how this can make the software development life cycle easier, cyclomatic complexity is also relevant in testing, because it can help us determine the number of test cases that are necessary for us to achieve comprehensive test coverage of a particular module. For example, if we have a method that has a cyclomatic complexity of 4, and we want to make sure that we are covering all of the independent paths, then we know that we have to write at least 4 cases to be able to have a comprehensive test coverage, when we're talking about coverage based on independent paths. All right, so another thing that will make our code high quality is scalability. And in here, again, we're talking about a lot of factors. We're going to go into a lot more detail in another session about scalability. But for now, hey, let's keep in mind that design and architecture will definitely affect the scalability of our code, the available resources that we have, scalability of external resources, and some things that are very particular about the code. For example, multi-threaded correctness in our code. And in here we have to understand how the particular runtime or how the particular language that we're using handles multi-threaded mechanisms. Multi-threaded is very different in Node.js than in Java. Multi-threaded code works very different in Python depending on how you're running Python. So here we need to have a good understanding of our runtime, good understanding of our code, to make sure that we are not making mistakes in, those crafty, complex, tricky section of the code where we could potentially have multiple threads interacting with each other. So, multi-threaded correctness in our code depends on the language, as I mentioned already. Static analysis tools, which is something that we'll talk on the next session, can help us detect issues in synchronization code. If we have synchronization code, for example, Node.js, because the way it's built doesn't have any synchronization because it is somewhat single-threaded, even though it has some multi-threaded functionality on the back. Good code review is vital. We want to make sure that senior developers or developers that have experience with multi-threaded code are reviewing those critical pieces of code. And finally, testability. High quality code is easy to test. And I think I've spent, maybe 2 hours before this just talking about testing, whether it's integration testing, unit testing. But the key takeaway here is that high quality code needs to be easy to test. High quality code should already include the test. We should have comprehensive tests that lower the risk of us making changes, because if we have good tests, we can make a change, we can run the test suite and figure out if we broke something else, something that we didn't think about. A good comprehensive set of tests is going to help us have more certainty about what we're doing. Okay, when we're talking about testability, we also want to keep track of how much are we testing? How comprehensive are our tests? And the way we do this is by measuring coverage. And we can measure coverage by line, we can measure it by branch, we can measure it by path. So what does it mean? When we're talking about line coverage, we're basically talking about how many lines of source code have been tested. Branch coverage, how many of the branches of the control structures, things like switch, if, have been tested. So if we have an if, we should be testing that at least 2 ways to be able to test the true and the false side of the branching statement. If we have a switch statement, then obviously it depends on how many cases we have. We can also measure the coverage in terms of the path coverage. This ties back to cyclomatic complexity. How many of the paths that we have identified when we were measuring cyclomatic complexity are tested by the different test cases that we have? Now, normally we are going to use tools, automated tooling, that is going to give us the coverage. It's basically telling us the percentage. It's going to tell us how many lines were covered, how many branches were covered. Normally, the tooling that we use, they focus on line and branch coverage. Path coverage is normally not used as much. It might be used on some very specialized industries where we have a lot of regulation, where you have things that are truly mission critical. But for the most part, line and branch coverage is where we are. And, as long as we are able to measure those two, we'll have a reasonable understanding of how comprehensive our tests are. So the idea is that all of the things that we were talking about, again, some are a little bit more subjective, more arbitrary, but a lot of the things that we talked about, we can put them into metrics. For example, we can put test results into metrics. How many are passing? How many are failing? Lines of code, physical, logical, coverage. Again, the percent of lines that were covered, the percent of branches that are covered. Or if you, want to take it a step further, the percent of paths that are covered. Cyclomatic complexity. How complex is each of the methods that we have? Duplicated lines. Some of the tools are going to detect blocks of code that are duplicated within our code base. Code smells. Some static analysis tools are going to give us a rundown of what kinds of smells we have and the severity of them. And some of these static analysis tools are even going to try to calculate the technical depth of those code smells. Basically, how long is it going to take us as a developer to fix all of those smells that we have identified in our code base? All right, so in summary, we want to use metrics to measure quality. We want to keep track of the metrics to reduce the risk, make sure that we address if we see that the metrics are trending in the wrong direction, make sure that we address that before it becomes too much of a problem. We want to focus on quality early on by having the infrastructure, by having the metrics, by having the automation in place. We want to obviously automate as much as possible because it can get tedious to, run the tools and look at the reports, things like that. And, at the end of the day, keep in mind, what are we focusing on? We're focusing on high quality code. Keep it, try not to make it personal. Try to use metrics to keep the conversation at an objective level and, use common sense to handle the more subjective, more arbitrary cases. All right, with that said, what are we going to talk about in the next video? We're going to talk about some of the tools that we can use to actually measure the quality of our code. In particular, we're going to talk a little bit about static and dynamic analysis, what that means, how we can use those techniques to get more data, to make sure that we catch bugs early on, things like that, to, again, at the end of the day, ensure that we have the best code possible. And with that said, thanks a lot for watching. Don't forget to subscribe, follow me on X or Twitter, follow me on Mastodon, take a look at my webpage, www.javaprocess.com, and I'll see you next week for the next part. Remember, where we're going to continue this conversation, take a look at some tools where we can actually put some of these things into practice. Thank you.